All right, it is my great honor to introduce our lecturer on quantum algorithms, Scott Aaronson. There's nobody else in the world I'd rather hear lecture me about quantum algorithms, so we're in for a great treat. Some of you know Scott's many influential contributions to our field, or maybe you've read his incredibly engaging book, Quantum Computing Since Democritus, or I hope you read his blog, Shtetl Optimize. It's a must-read for all quantumists. I guess the best way to sum up Scott's scientific worldview is with a limerick. Scott said to his students, "You see, NP is much larger than P. It's something I know, but it's too hard to show, so let's talk about post-BQP." Take it away, Scott.
Thank you for the beautiful limerick. Complexity classes are pretty easy to rhyme because almost all of them end with P, right? But and thank you for setting up expectations that I won't be able to live up to. But it's my first time in Boulder. I've been having a wonderful time here. I hope you have too. So I've met many of you over the last couple days and got a sense of what you would like to hear about quantum algorithms, what you know, what you don't know. What I think I'm going to do is just sort of give explain some of the most fundamental quantum algorithms that were discovered in the 80s and 90s, and that sort of set the much of the agenda of this field. Deutsch, Joseph, Bernstein, Vazirani, Simon, Shor, explain some of the basic conceptual questions that arise when we want to know, well, in what sense are these algorithms getting a speed up over a classical computer, right? And can we prove that? And under what assumption? And, so we'll have to distinguish between, counting the number of gates versus counting the number of queries to an oracle. Okay, so we'll talk about all of that. Grover's algorithm, some of its applications. And then if there's time, in the last lecture, I'll say something about this correlation algorithm, which is a very, very small quantum algorithm, but one of the only ones that I invented, I guess. I'm usually just trying to rule out quantum algorithms, right? So it's a bit ironic that I'm the algorithms lecturer, and next week you'll have a physicist, Toby Cubitt, lecturing you about complexity theory. Okay, but we'll have fun with it. Okay, and then by popular request, I'll try to maybe moderate a discussion of some sort about what is the potential for quantum algorithms to help with machine learning problems. Okay, as it happens, there was a very big result just a couple days ago that sort of affected that question by a student from UT Austin named Ewan Tang. I may say something about that. In fact, I was just blogging about it this morning right before I came here. But that doesn't mean you should open up my blog. You should listen to me. Okay? Okay. And stop me if there's questions, and so that there was a request for exercises. So anytime I don't feel like proving something, that's an exercise. Okay, and also I will try to note when things are open and when there are problems that might be appealing to a student. Okay, so what is the sort of the basic idea of quantum algorithms, right? Why did people, think about quantum computing in the first place? Why did they hope it would do anything better? Well, as we all know, if we have a state of n entangled qubits, then in general we need to describe it by a vector of 2 to the n complex numbers. Okay, so this was implicitly known. I mean, at least since Schrodinger wrote down the Schrodinger equation in 1926. But I think its implications were not fully appreciated until much more recently. To a computer scientist, this is maybe the central fact about quantum mechanics, right? That to keep track of 1,000 measly particles, nature has to maintain 2 to the 1,000 size scratch paper, right? That wouldn't even fit in the observable universe, And so we'd like to know, is that for real? If it is for real, can we do anything with it? Okay, but if you read almost any popular article about the subject, they will sort of jump immediately from that observation of exponentiality to saying something about how quantum algorithms work, which is wrong. Okay, and this is a boulder that I've been pushing up the hill for like 15 years, but it keeps rolling back down. Okay, but even sometimes people within our field who know better, fall back on the wrong way of explaining things when they are talking to the press. I mean, maybe just because they think that there's no better way, or but I think that there is a better way to talk about it. Okay, so the wrong thing that everyone wants to say is that, well, a quantum computer can just explore exponentially many answers in parallel, right? If you're an Everettian in different parallel universes, right? And that is why it gets an exponential speed up, full stop, right? If this was true, this would lead us to think that quantum computers, could, for example, solve NP-complete problems, the traveling salesman problem or whatever in polynomial time, just by, trying every possible tour, and then whatever branch happened to guess the right one would say, hey, everyone over here, I found it. So that would be pretty amazing. We wouldn't, it would be a lot easier for us in a way. We wouldn't have to think so hard to invent things like Shor's algorithm, or for that matter, Grover's algorithm, right? It would just be try everything in parallel. Okay, but, nature is more subtle than that. Right, the profile of what a quantum computer can do and what it can't do, well, we still don't fully understand it. Which is no surprise in some sense, because we don't even fully understand what classical computers can do and can't do. As John mentioned in his limerick, right? We can't even separate P from NP, for crying out loud. Okay, so of course we don't know, what is the ultimate potential for quantum computers, but the picture that's emerged over the last quarter century, I like to say that it's sort of more subtle than any science fiction writer would have had the imagination to make up. Okay, right? If you were just making up a science fiction supercomputer, you would just say, oh, it can solve NP-complete problems, it can solve the halting problem, whatever, right? You wouldn't make up something that can do factoring, but not finding short vectors and lattices. It's like, what? So, okay, so where does this weird profile of abilities come from? And that's very much the what we'll try to understand in these lectures. Okay, so the first thing to notice is that this feature of states being exponentially long vectors, in some sense this is not unique to quantum mechanics. Okay, that is true even of classical probability theory. Right? If I just have a classical randomized algorithm, and it makes n random decisions, well, guess what? Now I have a vector of 2 to the n probabilities to represent, everything that could have happened, right? So again, there's an exponentially long vector. Okay, but, with classical probability theory, you wouldn't normally say that exponentiality is out there in the world, right? Because after all, at some point, you've got to look at the computer, if you want to use it for something, and when you look at it, you only see n bits. You don't see, these 2 to the n probabilities. You never directly observe them, right? They're just sort of something that you can keep track of in your head to figure out which outcomes are more likely than others. And actually, something similar is true quantumly. Okay, we never directly observe amplitudes, but what's the difference? Well, it's that amplitudes are complex numbers, and they're normalized using the 2 norm rather than the 1 norm. Okay, and to say, sort of everything about, that is special about quantum mechanics, but certainly in particular everything that is special about quantum algorithms ultimately boils down to that, right? So, this is, it seems like I'm just saying trivialities, okay? But this is a fact that you can use. If someone is telling you about their awesome new quantum finance algorithm, their quantum genetic algorithm, their quantum neural network, okay, whatever it is, first question you should ask, where are the minus signs? Okay? If there's no minus signs, well, and let's say there's no use of the 2 norm, then there's no quantum speedup. Okay? That's actually a very useful thing to know. Okay, so the entire hope of getting a quantum speedup sort of is to exploit the way that amplitudes, being complex numbers, can interfere with each other. Okay, so if you want to look at it in, say, the Feynman picture, like a sum over paths, then to calculate the final amplitude for a quantum computer to produce some output, you have to sum over, a potentially huge number of contributions. Could be an exponential number of different contributions, okay, each of which is a complex number. Okay, but these different contributions to an amplitude can interfere constructively or destructively, right? If they're in phase with each other or if they're out of phase. Okay, the basic goal with every quantum algorithm, okay, every one that is useful or that sort of gets any advantage, is to choreograph the right kind of interference pattern. Okay, it's to set things up in such a way that for each of the wrong answers, some contributions to its amplitude are positive and others are negative, so that, or they point in different directions in the complex plane, more generally, so that they interfere destructively and cancel out. Whereas for the right answers, there might be more than one, but in any case, for right answers, you get constructive interference. Okay, if you can arrange that, then, of course, when you measure your computer state at the end, you will see a right answer with high probability, right? Perfectly if the interference was perfect, or, most of the time if the interference was imperfect. The tricky part in quantum algorithm design is always that you need to figure out how to arrange this, even though you don't know in advance which answers are the right ones. If you knew that, then there wouldn't be a lot of point in running the algorithm. Okay, so you need to sort of set, do a sequence of unitary transformations where somehow you will have a mathematical guarantee that by the end, the right answers and only the right answers will enjoy constructive interference, and the answers that are wrong will suffer destructive interference. And all of this has to be done faster than a classical algorithm could do the same thing. Otherwise, it's not very interesting. Okay, so that's the challenge. That's why this is a field that people have to have conferences about. Okay, and you could say nature just gives you this really bizarre hammer, this sort of interference choreography hammer, to mix metaphors. And Feynman and Deutsch and others were talking about this in the 80s, but it took more than a decade for people to really figure out, well, are there any interesting nails that this hammer can hit? Okay, and and then people finally started figuring that out in the 90s. And there was a beautiful sequence of discoveries that we'll go through in today's lecture, culminating with Shor's famous algorithms for factoring and discrete log, which I won't have time to fully present to you, but I'll say something about. That's why it's epsilon times Shor. Okay, so so just to orient ourselves, there were two main settings in which we can study quantum algorithms. Okay, and a major theme, major thing that I hope to help you understand, in these lectures is the interplay between these two different settings. Okay, so in some sense, what you ultimately care about in the real world, right, is just, the real resources that are needed to solve your computational problem. Okay, and that could mean, the most basic thing would be the number of gates, right? Do you need an exponential number of gates? Exponential in the size of the problem, well then that's not very good. Or can you do it with a polynomial number of gates, right? And that's what we hope for. Okay, one could also consider, the number of qubits that are needed, the number of parallel layers of quantum gates, and one can study other resources, but number of gates would be the most basic one. Okay, and so, we can talk about that in terms of complexity theory. This is not these are not complexity theory lectures, but I hope I can get away. Well, it's my talk, so I'm going to put some complexity classes on the board. Okay, but these are the only ones I'm going to put. Okay, QMA and all of those I'm going to leave to Toby next week. Okay, so just the sort of the most basic classes to orient ourselves a little. P, polynomial time, is the class of all the decision problems that are solvable by some polynomial time algorithm running on a standard digital computer, deterministic algorithm. Okay, so polynomial time means it always halts and it always returns the right answer on any input, in a number of steps that can be bounded by some polynomial in the length of the input. Okay, so examples of problems in P, I give you a graph. Is it connected? I give you an integer. Is it prime? That's a famous one. That was only shown to be in P in 2002, right? So, P has some very non-obvious things in it, right? I give you a graph. Does it have a perfect matching? Linear programming is in P, right? I mean, most of what we try to do with our computers on a day-to-day basis is in P, right? And this is, this already means something for quantum algorithms, right? That like every week, at least before I had my journalist moratorium, I would be on the phone with some journalist saying, but how is quantum computing going to change the way that we send and receive email, and that we do word processing, and that we play video games, and and they list off all the things that they know that computers are used for. Well, the trouble is most of those things are in P, right? And that sort of limits the quantum speed up that you could hope to get, typically to a polynomial speed up, unless you want to talk about algorithms that don't even have to look at the whole input, which which we'll do as well. Okay, but so there's a slight generalization of P, if you like, called BPP. Stands for bounded error probabilistic polynomial time. Okay, and this is just informally the class of all the decision problems that are solvable in polynomial time by a randomized algorithm. Right, a classical algorithm that has some source of random bits, independent of the input, but it can use those random bits to sort of make random choices if that helps it, and sort of average over, this sort of smear out the sort of bad cases, or sort of deal with sort of bad inputs where a deterministic algorithm, it might be that for any deterministic algorithm there are some inputs that make it get stuck. Right, but if we can randomize over, our choices, then sometimes we can arrange so that for every input we have, let's say, at least a 90% chance of getting the right answer. Okay, and a crucial point is that, as soon as we have, like, if we're trying to solve a decision problem, as soon as you have any probability of getting the right answer that is bounded above a half, then you're done. Okay, because then if you want a if you're not happy with that success probability, well then just run your algorithm several times and take the majority vote. Okay? That's called amplification, right? That's one of the most basic tricks of algorithm design, right? So often people would define BPP by saying your randomized algorithm needs to succeed on every input with probability at least 2/3, right? The choice of 2/3 is completely arbitrary, right? It could, just as well be 2 over pi. Or whatever. Okay. cosine squared of pi over 8, if you prefer quantum numbers. Okay, so but now, importantly, for the last couple of decades, most computer scientists believe that ultimately BPP is equal to P. Okay, and the reason is that there was a series of breakthrough results in the 1990s, which basically said that as long as there are sort of sufficiently hard computational problems, sort of hard enough problems for Boolean circuits, and it seems like there clearly are, then you could use those hard problems to create pseudo-random generators, okay, which will then be as good as true randomness for any polynomial time randomized algorithm, right? So for a probabilistic algorithm, right, there's always something you can do with it that we can't do with a quantum algorithm. Okay, and that is you can always just sort of pull the randomness out of it. You can always think of the randomness used by a classical randomized algorithm as just some auxiliary input, right? It's just some auxiliary sequence of zeros and ones that once you fixed it, the algorithm would be deterministic, right? And and then you can start playing games with that. Okay, well, you could say, well, what if instead of giving my randomized algorithm the true random bits it expected, I gave it some pseudo-random bits, and I generated from some small seed, and then I looped over all the possible choices for that seed, right? You can play games like that, and we now know that under very, very mild assumptions, those tricks would be strong enough to show that BPP is equal to P. Okay, so so you could say like the whole story of quantum computing challenging the extended Church-Turing thesis, challenging the view that P is what we can do in P exhausts what we can efficiently solve in the physical universe. We sort of already had a close call. Right? BPP was already sort of a challenge to this thesis in the 1970s, except, it looks like, P still, reigns supreme, right? It is not, actually BPP is probably not, it may let you, randomized algorithms may give you polynomial speedups, but if these conjectures are true, then not exponential speedups. Okay. Then NP, non-deterministic polynomial time, consists of all the problems for which we can efficiently recognize a solution if the answer is yes. Okay, a famous example of an NP problem would be factoring. Right? Let's phrase it as a decision problem. Like I give you an integer encoded in binary. I ask you, does it have at least 3 prime factors? Right, or some question about its prime factorization. Now that question might be very hard to solve, might take you exponential time to solve it, but if someone wants to prove to you the answer is yes, they can just show you the factors. Okay, you check them yourself. Okay, that is the defining property of an NP problem. Okay, so any problem in P is also in NP, because then you don't even need someone to give you this magic answer. You just find it yourself, right? And of course the foundational conjecture of complexity theory is that NP has some problems that are not in P, right? Where someone could give you the answer and you could check it and say, wow, that's really good. It's hats off to that, and you could not have efficiently found it yourself. Okay, that is the famous P not equal to NP conjecture that, I like to say that if we were physicists, we would just call it a law of nature. But, there's in an interdisciplinary field, there can be differences in terminology. So what's called a law in some fields is called a conjecture in others. Okay, so okay, now the hardest problems in NP are called the NP complete problems. In some sense, these would be, the holy grail of quantum algorithms research, right? And these are what all those popular articles mistakenly say that that we know how to do with a quantum computer. Okay, so most optimization and constraint satisfaction problems that you ever would have heard of, satisfiability, bin packing, airline scheduling, Sudoku. I think most classic Nintendo games, fall, as well as, things, that are of less practical interest, right? Like, finding some financial model, whatever, that explains your, so these can all be shown to be NP complete, which means simply that if you had a polynomial time algorithm for any one of them, then it could be converted to a polytime algorithm for every NP problem, and then P would equal NP. Okay, that's what NP complete means. BQP, I drew it with this wavy boundary because everything quantum is spooky and weird. But so it generalizes P and BPP. This is just saying that a quantum computer can always simulate a classical one, right? You just just use Toffoli gates. In fact, don't even have to use any Hadamard. Well, if you want to simulate a randomized algorithm, I guess you should use some Hadamard gates to just get your randomness. But you can sort of like you could use a space shuttle to taxi around a parking lot. You could use a quantum computer to simulate a classical one. Okay, the interesting question is, can you do more than that? How much more? The famous discovery of Shor is that BQP contains at least some problems, famously factoring in discrete log, that we don't know to be in P or BPP. In fact, we base a lot of the world's electronic security on the belief that these problems are not in P or BPP, for better or for worse. Okay? Now, factoring, very importantly, is not believed to be NP complete. Okay, it has a lot of special structure that seems to preclude its being NP complete. Okay, so as far as anyone knows, factoring is one of these problems in this sort of intermediate zone, this demilitarized zone or something between P and NP complete. Okay, now this zone, you might first think, okay, it's just some sort of catchment basin for weird problems that we can't classify. But if we're trying to get big speedups with quantum algorithms, this zone is one of the main places where we have to look, right? Because if we don't think that there's going to be a fast quantum algorithm for NP complete problems, well, then we need to go below there, right? We need to look at the problems that have special structure of one form or another that prevents them from being NP complete. Okay. In the other direction, no one knows whether BQP is contained in NP. Okay, so there could be problems that a quantum, even decision problems that a quantum computer could efficiently solve, but for which a classical computer could not even recognize the answer, let alone find it, right? Quantum simulation might be a good real-world example of that kind of behavior. There's a generalization of NP called the polynomial hierarchy. There was a breakthrough a couple months ago when we got sort of the first formal evidence that BQP might actually go outside of the entire polynomial hierarchy. Okay, I'll tell you about that if there's time in the third lecture. Okay, and then all of these classes are contained in what we call Pspace, okay, which is everything you can do with a classical computer using a polynomial amount of memory, but possibly reusing that memory over and over for an exponential amount of time. Okay, that's Pspace. It turns out that it had to be shown by Bernstein and Vazirani in their paper where they first defined BQP and studied its properties. But the intuitive reason is the Feynman path integral, if you like, right? The reason why BQP is in Pspace is that you could take an amplitude that interests you in your quantum computation and express it as a sum of exponentially many contributions, each of which is individually easy to compute. Okay, right? By just sort of expanding everything out. Every time a gate is applied, that multiplies the number of terms by some factor. Okay, but you end up with some giant set of terms that has to be summed, just like in particle physics. I gather this happens, and then you could sum all those terms, reusing the same memory over and over for exponential time. Okay, that's basically why BQP is in Pspace. That already has an important implication for quantum algorithms. Okay, because computer scientists seem very, very far right now, even from being able to prove that P is not equal to Pspace. Okay, let alone P is not equal to NP. Right, and so when people say, "Well, give me a quantum algorithm with a proven speed up over classical," right? In this setting, the setting of computational complexity or gate complexity, that is just too much to hope for in the present state of mathematical knowledge. Okay, because we can't, for crying out loud, we can't even prove P is not equal to Pspace, right? So how on earth could you prove that P is not equal to BQP without because BQP is sandwiched in between them, right? So this is why we cannot hope for sort of unconditional exponential quantum speedups, not requiring any hardness assumption, right? In this gate model, in our present state of mathematical knowledge. Okay, and again, the popular articles almost all get it wrong, right? So quantum computers do factoring, they do this and that, they do all these problems that are known to take exponential time classically. Well, sorry, we can't even show that anything in Pspace takes exponential time classically. Okay, we can assume it, and and that is what we like to do, right? Yeah.
Can you repeat the definition of NP complete?
Yeah, NP. So a problem is NP complete. The technical definition is if number one, it's in NP. Okay, so I'll write it. Let's say problem A is NP complete if A is in NP, and we could say all of NP could be solved by a polynomial time algorithm if I gave you a magic box for solving a problem, for solving A for free. Okay?
It's confusing, but then wouldn't that make that kind of a problem not NP? If it's polynomial.
No. Okay. So let me say this again because this is important. Okay. Defining property of an NP problem is that you can recognize the answer if someone shows it to you. NP does not stand for not polynomial. Okay, if you remember nothing else from these entire lectures, okay, NP does not stand for not polynomial. Okay, it stands for there is a witness for a yes answer. Okay, so if P is equal to NP, well then guess what? Every NP problem is also a P problem, right? And and then every NP complete problem would be in P, right? So the NP complete problems, are the problems where proving that those problems are not in P is just equivalent to proving P is not equal to NP. Okay. Yeah.
So if P equals BQP,
yeah.
does that mean there's a certain kind of hidden variable model?
Well, you could choose to say that if you wanted to. I mean, it would mean that sort of quantum mechanics, at least, as insofar as you just wanted the expectation value of a particular observable, right? Let's say, like a Boolean yes or no. Anytime you wanted that, there would be a fast classical algorithm to give it to you. Right? Now there's still a technical issue, which is that might not imply that you would have a fast classical algorithm to sample from any probability distribution that a quantum computer could efficiently sample from, right? But if you had that stronger thing, then you could think of it as a kind of hidden variable model, right? So, in some sense, what we're trying to, if you want to prove that BQP is stronger than P, you could say it is sort of like proving a massively jacked up version of Bell's theorem, right? Except, now instead of caring about locality, we care about polynomial time computability. Yeah.
So you mentioned optimization problem. because I also thought that this thing is for a decision problem. Is it
Yeah.
that you can always rephrase optimization problem in terms of decision problem? Like, is there a
Yeah,
collaboration with
that is exactly right. So, it is only for convenience that computer scientists like to formulate these classes in terms of decision problems, right? An optimization problem can be easily rephrased as a decision problem or let's say as a sequence of decision problems by just doing a binary search, right? You say, is there a solution that's this good? Okay, there is. How about a better one, right? And so forth. Okay, another fundamental observation is that for the NP-complete problems, just deciding whether a solution exists, if you're able to do that, then you can also find solutions whenever they exist. And the way you do that, all right, you know what? It's an exercise. Okay? That's true of NP-complete problems, although it's not true of every problem. So for example, if I give you a game and I ask you to find a Nash equilibrium, right? That is now thought to be probably a hard problem, probably outside of P. Right, there was a breakthrough result a decade ago addressing this. Okay, but the decision version, is there a Nash equilibrium, is quite easy. Why is that, anyone? Yeah. Yeah, because the answer is always yes. That's the thing that Nash proved, right? If you saw that movie, A Beautiful Mind, well, it didn't explain it, but Nash proved that the answer to the decision problem is always yes. Okay, but finding a solution could be harder. Okay, but that's for a special problem, like Nash equilibria. For NP-complete problems, decision and search are equivalent. That's an exercise. Okay. So we can't sort of hope. Okay, so you could say, just staring at this picture, two things become immediately clear. Okay, number one, you could say, well, look, we can at most hope for an exponential speed up with a quantum computer, right? And no more than that. Like, for example, quantum computers are not going to take uncomputable problems like the halting problem, and make them computable. Okay, why? Well, because everything in BQP is also, solvable certainly by a classical computer with exponential time. Okay, exp is just what you can do in classical exponential time. Right, you could just write out the whole wave function or something. So you could at most get exponential speedups. And also we see from this picture that all the speedups that all the more than polynomial quantum speedups that we could ever get are going to depend on unproved conjectures about problems being hard for classical computers, right? Why? Because we can't currently prove even that Pspace is larger than P. Okay, having now explained all of that to you, now next I'm going to tell you how you can get more than exponential speedups with a quantum computer and how you can prove them unconditionally. Okay? The way to do it is to switch to a different setting of quantum algorithms, which we call the setting of query or black box complexity. Okay? And in practice, this is, I would say the majority of the thinking about quantum algorithms that actually happens in the second model. Okay? So what is the difference between the two? Right. Well, in computational complexity, you assume your input is just given to you. Let's say it's some n-bit string. Typically we'd assume you have enough time to read the whole input, right? And then you want to learn something about it by doing a sequence of operations. In a quantum computer, we take our elementary operations to be 1 and 2 qubit gates, let's say, or maybe 3 qubit, like the Toffoli gate. Okay, I understand that you already heard about gates and universal sets of quantum gates in this course. Is that true? No? Okay. Okay, so we just like with classical computing, you want once you have a rich enough set of Boolean operations, and it doesn't have to be very rich, like and, or, and not would do the trick. The NAND gate by itself would do the trick, right? Then just by composing enough of those things, you can express any Boolean function that you want. Right, is a number prime or composite, right? Will Windows crash under these circumstances? Okay, right, everything can be boiled down to, and or not gates, at least if you fix the size of the input, okay? It's when the input size, can be arbitrary and you want a single algorithm that works for any size of input, that's where you have to start worrying about Turing machines. Okay, but computer programs with loops and conditionals and all those kinds of things. Okay, but if your input size is fixed, then you might as well think of your entire computation as simply a circuit. Okay, meaning a collection of elementary logical gates that you then compose together to get whatever function you want. Okay, and so that's true classically. That's also true quantumly, right? And in fact, the class BQP, when you go to formally define it, right, you do, the easiest way to do so is in terms of quantum circuits. Okay, and basically the trick is you just say BQP is the class of problems for which you have an algorithm running on your classical computer that, given an input, will sort of output the quantum circuit that you should run for that input. Okay, and the quantum circuit has polynomial size, and it usually tells you the right answer. Okay, that's basically the definition of BQP. Okay, so it stands for bounded error quantum polynomial time, right? So and this actually corresponds pretty well to how quantum computers would probably be implemented experimentally. Okay, right? It's like there's often people want to talk to me about quantum programming languages, which is a field, and there are many interesting things to say about how exactly you program a quantum computer. Okay, but then they want to say, well, and then how does the quantum computer handle all the control flow, the loops, the conditionals? Okay, but in practice, you can almost certainly just offload all of that stuff to your classical computer, right? This is something to always bear in mind, right? Whenever you're thinking about quantum algorithms, whatever the classical computer can do, for God's sakes, let the classical computer do it, okay? Because it's just going to be so much easier, so much more reliable, right? That part already exists. Okay, so all you'd have to do is sort of give an algorithm for your classical computer that sort of tells your superconducting system what couplings to have between which qubits at which time, or that tells your ion trap system where the laser should be aimed, or things like that. So that's that's a way to think about what is a BQP algorithm, right? What does it mean to put a problem in BQP? Okay, and so just like in the classical case where like the and, or, and not gate suffice, so too in the quantum case there are very nice sets of 1 and 2 qubit gates that have the property of universality, okay, which means that you can, by just composing enough of those gates, you can approximate any unitary transformation on any number of qubits to any desired precision. Okay, that's what universal means in the quantum world. Or sometimes maybe not. Like maybe you only get orthogonal matrices, like involving real amplitudes. But then that would be enough to solve every problem in BQP. Right? So even if you don't have the sort of physical universality to get every unitary, you may get a subset of unitaries, into which any quantum computation could be encoded, right? And that we call computational universality, and that is also enough to build quantum any quantum algorithm out of. Okay, so in this world, we apply a sequence of 1 and 2 qubit gates. At the end, we can make some measurements. Let's say if we measure some qubits in the 0-1 basis, and then we use that to determine, what the algorithm will output. Possibly after some classical post-processing, if you like, which of course should also run in polynomial time. Okay, so that is the the gate model, if you like. Okay, now in the query model, here we imagine that there is some function. Okay, maybe a function, mapping n-bit strings to integers or something like that. Okay, this function could have exponentially many different values, right? So it could have, an enormous domain. Okay, and somehow you have been given the ability to compute this function. Okay, in the real world, that would probably mean that someone has given you a piece of code that, when you run it on any x, it computes f of x. Okay, but what we do in this query model, in this query setting, is that we think about it more abstractly. Okay, so what we do is we just imagine that you have a black box. Okay, that when given any x, could output f of x. Let's say, and then the resource that we care about is the number of queries that you need to make to this black box in order to learn some property of it of interest to you. Okay, for example, maybe you'll be told that f is a periodic function, and your goal will be to find its period. Okay, or maybe you'll just want to know, is there any x such that f of x equals 1? Right, that would be a way to encode the problem of search. Okay, so in the black box model, we consider quantum algorithms that look like this. Okay, so the algorithms consist of an alternating sequence of queries, what we call query transformations, and unitary transformations that don't depend on f. Okay, so what is a query transformation? So, given this function f, I'm going to define a unitary q sub f as follows. It will act on computational basis states that could look like, x, a, w. It could have 3 registers. X is an input, for which we want to know f of x. A is called an answer register, for storing the result. W is just whatever workspace you want to have that does not participate in this query. Okay, and what it does is that it takes f of x and it exclusive ORs it into the answer register. So, this just means like if f of x has many bits, then I just do a bitwise exclusive OR, right? So if a, was initialized to all zeros, then I just get f of x here, right? But, why do I have to define queries in this roundabout way? Well, for one thing, because it has to be a unitary transformation, right? This is quantum computing. Okay, so I can't just say write f of x here. That would not be reversible. That would not be unitary. Okay, but this definition actually has a further nice property, which is that if you had a small quantum circuit to compute f, like let's say you had a network of Toffoli gates, that could quickly compute f, then you can actually quickly implement this transformation. Okay, why? Exercise. Okay.
If it's a black box, why does it need workspace?
Oh, well, I mean, because this might be just one step in some larger algorithm that is going to be storing some other stuff. In fact,
It doesn't have to touch the other stuff.
yeah, well, the query is not touching the other stuff, but in between queries, maybe we would do stuff, do something that would involve this. In fact, we have examples of this. Ambianus's algorithm for element distinctness. is a notorious example of a quantum algorithm in this query model where it requires a very large workspace, and no one has been able to figure out how to get rid of that. Okay, there, open problem. Okay, project for anyone who is interested, right? By now we actually, after sort of 25 years of work on this, we actually understand a great deal about quantum query complexity. That is the number of queries that quantum algorithms need to compute various properties of functions. There's plenty that we still don't know. Okay, but one area where we know almost nothing is what are the trade-offs between the number of queries and how many qubits, how many auxiliary qubits of workspace you might need. And so that's we're just missing the techniques to understand what the optimal trade-offs are. Okay, so so this is unitary. It can actually be realized, if you had a fast way to compute f. So this is a convenient way to think of queries. Now there's another way, another type of query that that is often more convenient in practice. Okay, and this type is used if f happens to be a Boolean function. Right? If it happens to just take two values, then it often turns out to be convenient to consider queries that they do something that wouldn't even make sense in the classical world, which is that they take the answer and they write it into the amplitude. Okay? This is called a phase query. Okay, so all this is saying is for each basis state, flip the amplitude if and only if f of x is 1. And then A here I'm thinking of as a control qubit that is controlling whether or not a query should even happen at all. Right? But if A is set to 1, then this is just saying for every basis state, flip the amplitude, if f of x equals 1, do nothing if f of x equals 0. Okay? Now, so which type should we use? Well, it turns out that these are equivalent. So for a Boolean function, I can always use a phase query to simulate an XOR query, and vice versa. Okay, either can simulate the other. Why? Exercise 3. Okay. The equivalence of the two types of quantum queries. Okay, how do we, by appropriately doing something with this qubit over here, for example, can we make one simulate the other? Yeah. Oh yeah, no. So I agree, and in fact we will be considering non-Boolean functions. I'm just saying if your function happens to be Boolean, then there's this other type of query that's equivalent to the first type.
If it's not Boolean, let's say you can take 4 values. You can just, instead of mapping in the 2 rooms, you can map that into the 4. You could, but then but on the other hand, in that case, I don't think we would have this equivalence. Okay.
If you would like to investigate, what type of phase queries, or for what kinds of phase queries could we have equivalence for many valued functions, maybe that could be a good project for somebody. Okay.
So
Yeah.
what's the point regarding the trade-off between queries and qubits?
Well, just that for some quantum algorithms, we there are many, the quantum algorithms that we know that minimize the number of queries, need a large workspace, and we don't know whether that is necessary or it's not. Okay.
But isn't the query complexity defined just given unlimited amount of weak sources?
It is, yes. So that's why, and so then that's the first thing you study. But then once you know the answer, then you can go and ask something else. Okay. So now, crucially, so what we can do in this model is that we can, apply these query transformations. Now, notice that these query transformations are self-inverse, right? Which means there's never any point in applying 2 of them in a row. Okay, so in between, every 2 query transformations, we should imagine that the algorithm is doing something else. sort of set things up for the next query. Okay, and these are these U0, U1, U2, and so forth. Okay, now crucially, in the query complexity model, we allow any unitaries whatsoever, on any number of qubits, right, in between the queries. Okay, so we don't care how many gates it may take to realize them. Okay, so we're only concerned with the number of queries. Okay, yeah.
Maybe you explain this.
Yeah.
I mean, the point of this thing is like somehow you write your algorithm in terms of this unitary plus a query, and then eventually you do something that gives you the answer.
Yes.
That needs the information of the.
Yeah, right. We're interested in how many queries are needed to sort of extract the relevant information from F. And how does that compare to the number of queries that would be needed if we just had a classical algorithm that could just examine F on one, input at a time? Okay, that's what interests us. So why, the query complexity model may seem strange the first time you look at it. So why do we? What are the motivations for looking at it? If you want a buzzwordy, trendy thing, right? It captures the setting of big data. Okay, so one way to think about it is, imagine that I've got like some gigantic external memory, right, where X is just an index, a memory pointer, and then I would look up in some giant table, what is the value of f of X? Right? Often you have, enormous amounts of data. You would like algorithms whose running time is much, much smaller than the size of your, than the amount of data that you have. Okay? And query complexity, is an excellent tool for capturing that kind of situation. Okay? Number two, I'll call it opaque subroutines. Okay? So, very, very often in algorithm design, you have a subroutine. You know that it does something, but you don't understand its internal structure. Okay, or you don't want to have to, know its internal structure, right? So, for example, think about cryptography, for example, right? So imagine that you were trying to solve the problem of getting billions of dollars of Bitcoin, okay, by solving its proof of work. Okay, right? So what you have to do is you have to find inputs, that hash to particular values, right? You need to invert a hash function, where of course the difficulty of inverting it steadily gets harder as people spend more and more of the world's resources on this task. Okay, but now from one standpoint, right? This hash function is just a piece of code that is explicitly given to you. Everybody knows what it is, right? You could imagine doing all kinds of trickery to try to get an advantage. In fact, if p were equal to np, then that would precisely mean that you could just inverting the hash function would be no harder than or only polynomially harder than checking that that someone had done it, right? Which would mean that you could completely break Bitcoin. Okay, so okay, but now if someone asked you like what is the fastest possible algorithm, right, for inverting this Bitcoin hash function, the only honest answer you could give would be I don't know, right? It's I can't even prove p is not equal to np, right? There's you'll need at least a linear number of gates and at most an exponential number, and between the two, right, is a realm of dragons and of mystery and wonder. Okay, but now, we can say, well, but what do people actually do in practice? Well, in practice, this hash function was specifically designed to be as obscure as possible, right? It was designed so that the only thing that people really know how to do with it is just keep evaluating it on one input after the other, and and see when you find one that works. Okay, but as soon as you say, I'm going to restrict my attention to algorithms of that kind, then you are in the realm of query complexity. Okay, and there was and crucially, this is a model that we are much more able to understand in our current state of knowledge. Yes.
So how does this, the number of queries is related to the number of the gates? Because
Okay.
the gate, you want to implement it with the gate.
Right. Okay, good. I was about to talk about that. Okay, so that was in my okay, so motivation number 3 is that if you look at the quantum algorithms that we actually know, not all of them, but most of them actually fit beautifully into the query complexity model. Okay, and in particular, that is true of both Shor's algorithm and Grover's algorithm. Okay, in the core of both of them is an algorithm for solving one of these black box problems, and we're going to see that. Okay, but now, of course, as we just heard, of course, ultimately we want to know about the number of gates needed to solve a problem in the real world. Okay, but query complexity does tell us something about that. Just like I understand that, like, you have these things like perturbation theory, right? That, it tells you something about, what you really want to know, right? So this is our perturbation theory. Okay, so empirically, it turns out that the number of gates that you need in a quantum algorithm, let's say, is usually not much more than the number of queries. Okay? And we're going to see that that is true, for example, both with Shor's algorithm and with Grover's algorithm, right? That sort of there is a query problem that's at the heart of it, that you have to design a quantum algorithm that does, learn something about a function f by making few queries to it. But then, you might worry about these unitaries in between the queries, but fortunately it turns out that they're, quite easy to realize, right? That they too can be realized with a small number of gates, by doing something like a quantum Fourier transform. Okay, so this is not always true. In fact, I think we'll even see an exception to it. Okay, but it's often enough true, right? That you can just start if you're trying to design a quantum algorithm. A good start would be to just get a low number of queries. Right, and then worry about implementing it in terms of gates. Okay, and now motivation number 5 is that at any rate, the number of queries is a lower bound on the number of steps that you need. Right, because each query is itself a step. Okay, so if you want to rule out that there's like a fast quantum algorithm for learning some property of your function f, right, then it is enough to show that any quantum algorithm has to query f many times. Right? Once you've shown that, then it doesn't matter how many gates you might need, right? I mean, you've right, if you need exponentially many queries, then for sure you're going to need exponential time to solve that black box problem. Although the converse is not always true. Yes.
So we're number 4.
Uh-huh.
By how much more do you sort of reduce the
Okay. Let's say is it most polynomially larger than? Okay. That's what I mean. See, you'll have to stop me if right, because like often I just get into a zone where like I don't even see polynomial factors. Okay, just right. When I say not much more, I mean, is it most the number of queries times some polynomial in n factor. Yeah. Yeah.
Usually do you worry about the number of gates inside each query function?
Oh, well, right. Well, the whole point of this query model is that you assume that the ability to compute f is simply given to you, right? So now, of course, when it comes time to design a full quantum algorithm in the real world, then at that point we will have to worry about, well, how is this, how is f actually computed, right? But then, we know something useful that I mentioned before, which is that as long as we've got an efficient algorithm to compute f, right? So then, once I have a query algorithm, in some sense, the problem of giving a fast algorithm in the real world is reduced to giving an efficient algorithm for f, right? So then, all I have to do is then show how to implement f efficiently, and then I can implement each of the queries efficiently, and then I have an algorithm that is overall efficient. Okay, that is exactly what happens in Shor's factoring algorithm, to take one example. Okay? Yeah. In the what? In indefinite causal order. I think I'm going to, I would say that I'll defer that to later, but I'll defer it to some causally unordered, relative to me region of the universe. No, we can talk about that later. I mean, I don't think that, I've read some of those papers. I don't think that any of it matters for talking about, number of steps to solve an actual problem, right? It's sort of like it's almost like a programming language issue about how do you sort of, arrange things internally, right? But it's not going to matter for anything that we're talking about. Okay. So, okay, so with all of that ground clearing, I'm finally ready to show you a quantum algorithm. All right, so let's start with Deutsch-Jozsa, which in some sense was the first interesting quantum algorithm to be discovered, for some definition of interesting. Okay, so here, this is going, essentially all the quantum algorithms that we'll see will be black box algorithms, right, query algorithms. Okay, because, as I said, this is the model in which we know the most. Okay, so in the case of Deutsch-Jozsa, our black box is going to be a function that maps 1 bit of input to 1 bit of output. Okay, and our goal will be to learn the exclusive OR of the 2 bits. F of x, so f of x plus f of y mod 2, if you like. Equivalently, we just want to know, is f of x equal to f of y or not? Okay? Classically, how many queries to f are necessary and sufficient to solve this problem? Anyone? 2. All right, I see people just raising 2 fingers. Good. This is not a trick question. Yeah, you got to look at both of them, right? Either one could, unilaterally change the answer. So, you better look at both. Okay, so we could say that the classical query complexity, deterministic or randomized, of the Deutsch-Jozsa problem is 2. All right, now behold the wonder, because I'm going to show you that the quantum query complexity of the Deutsch-Jozsa problem is, can anyone guess? 1. 1. Okay, I mean, it's got to be an integer. It's, it can't be 0. We got to, it's going to be less than 2. Right? Yeah, okay. So, all right. So how do we solve Deutsch-Jozsa using 1 quantum query? Okay, and we're, this notion of phase query is going to be useful for us. Okay, so you'll see why I defined it. Okay, so let's start. We're only going to need 1 qubit for this thing. Okay, so our qubits conventionally start in the 0 state. Okay, now one of the best tricks I know in quantum algorithms research, we'll see it again and again, is whenever you're stuck for what to do next, try Hadamarding your qubits and see what happens. All right? So we're going to do that. All right? Let's just get some superposition going here. Right? By the way, just to remind everyone, Hadamard is this 2x2 matrix. Okay. Now, what should we do next? Anyone? Yeah, let's make a query, right? If you've already Hadamarded and you're still stuck, try making a query. Okay? Let's do that. Okay. Now we've made our query. Good. And this is going to be a phase query, by the way. Okay? Now what should we do next? Yeah, well, again, let's apply our rule, right? We've already queried. We're stuck. Hadamard. Okay? So let's Hadamard. And then let's just measure. Okay? So this is like the simplest quantum algorithm that there is. Let us understand what it does and why it works. Well, after I Hadamard, I've got a superposition of 0 and 1. Right? You agree? Now I do a phase query. What does that do? Well, that just writes f of 0 and f of 1 into the phases of these two basis states. So now I've got minus 1 to the f of 0, 0, plus minus 1 to the f of 1, 1, over root 2. Okay. And now, well, what is that? Anyone? Well, look, first suppose that f of 0 is equal to f of 1. Right? If they're equal, then these are either both positive or both negative. So what state do I get? Well, I get the plus state. Right? I get either 0 plus 1, or I get minus 0 minus 1, which, since global phase is irrelevant, is the same damn thing. Okay? So I get this or this. Now, next let's suppose that f of 0 is different from f of 1. Then what do I get? Anyone? Minus. I get either minus or minus minus, which again is the same thing. Okay, and then I Hadamard it, and then what happens? Yeah, this goes to 0, this goes to 1, and I'm done. Okay? One query. Yeah?
Let me just ask
Yeah.
that's the definition there. There was also
Oh yeah, okay. So we just set that to 1. Just consider, so that's needed for technical reasons. Sometimes you want certain basis states to not make any query, but in this case we wanted them all to query, so we just set it to 1. Okay, good. Okay. All right. Maybe slightly more interesting. What if I have n bits? Say x1 up to xn, and I wanted to know the exclusive OR of all of them. Then how many queries would I need to do that with a quantum computer? Let's just say just using the algorithm that you've already seen, right? Let's say that I want to know the parity of 10 bits, right? Like, I'm given 10 bits. Is there an even or an odd number of ones in them? How many quantum queries could anyone do that with? What? Well, yeah, so the first thought you might have is that, well, oh, gosh, I could just take this Deutsch-Jose algorithm and just apply it recursively, right, and just keep doing divide. Well, except if it was recursive, then it should just be like 1 times 1 times 1, and then it would just be one query, right? That sounds amazing, but that's sort of too good to be true. Well, what goes wrong if we try to apply the Deutsch-Jose algorithm recursively? This is a little bit subtle, but it's actually an important point. Can anyone see it? So why can't I just take like a Deutsch-Jose of Deutsch-Joses to get the parity of 4 bits with one query, for example? Yeah. Well, I think that's sort of gesturing in the right direction. The issue is one of the biggest banes of quantum algorithms, which is what we call garbage. Okay, garbage just means any information that you have lying around that prevents interference where you want there to be interference. Right? In this Deutsch-Jozsa algorithm, right, I mean, we can understand what is going on in terms of interference, right? That sort of when f of 0 equals f of 1, then and I Hadamard this plus state, right? Then the 0 enjoys constructive interference, right? And the 1 suffers destructive interference. So then I get 0, right? Conversely, if f of 0 and f of 1 are different, and I Hadamard, then the 1 enjoys constructive interference and the 0 suffers destructive interference, right? But in order for interference to happen, one thing we know in quantum mechanics is that your superposition has to be coherent, right? There can't be anything else lying around, okay? And what turns out, all right, I'm going to give this as an exercise. Okay, see what happens when Deutsch-Jozsa is applied, when you try to apply the Deutsch-Jozsa algorithm recursively, and see that the need to get rid of garbage is going to force you to multiply your number of queries by a factor of 2 at each iteration, so that you get really no advantage at all anywhere below the very first iteration. Yeah. All right, good. Well, good. So if you're not confused about that, then don't do this exercise, okay? It's just, if you're confused about it, then do this exercise to get unconfused, okay? Yeah. Okay, but one thing that you can do if you have n bits, well, you can get, if I want to get their parity, right? And parity is interesting as kind of, it's often, for many models of computation, it is like a max, it's a very hard problem. I mean, of course, for a real computer, right, you just go through and you count and you keep track and it's pretty easy, right? But for many sort of parallel models, it's a very interesting problem, okay? But I claim that at least there is always a quantum algorithm that computes the parity of n bits using n over 2 queries. How do I do that, anyone? Yeah, I just break up the bits into n over 2 pairs. I run the Deutsch-Jozsa algorithm separately on each pair, right? And then, I can just take the parity, I can just calculate the parity of all the results for myself. That doesn't cost me any additional queries, right? Because, I just have those bits now in my memory, right? So then this is how I can always get, quantum algorithms can give me a factor of 2 speed up for computing the parity of n bits. Okay? You might wonder, well, is there any quantum algorithm that does better than that, right? So now we have a well-defined question, right? We're just asking, is there any choice of this U0, U1, U2, and so forth, where you'll end up learning the parity of all the different values of f, like with fewer than n over 2 queries. Okay? So the answer turns out to be no. So it's a very beautiful theorem that for this problem, calculating the parity, the Deutsch-Jozsa algorithm is optimal. Meaning, a quantum computer can give you a factor of 2 speed up, but no more than that. Okay, so if this was the best quantum speed up that we could find, then let's all go home and forget about trying to build a quantum computer, right? Factor of 2, not very impressive. We're going to see some better speed up shortly. Yeah.
Can you explain that problem again? So like, do you want to compute the parity of x1 to xn, or to f of x1 to f?
Okay, good. So there's when we do query complexity, there's always 2 different ways to think about it, okay? And I may freely switch between the 2 different ways of thinking. What I'm really doing here is I'm imagining that we have a function, let's say f of I equals x sub I, right? That would just return the ith element of this table. right? And then I just want to know the parity of all the different values of that function f, right? But sometimes it's more convenient to think about it as a function, that has this, all these different possible values, which I could arrange in a table. And sometimes it's more convenient to think of that table of all the possible values as simply being a gigantic string, right? So in query complexity, we do both. Okay, does that answer? Okay. Okay. Okay, so I've got time to show you one more quantum algorithm. Okay, and this is going to achieve a more impressive speed up than Deutsch-Jozsa, although still not as impressive as we really want. Okay, but and here we're going to introduce something that we'll later see over and over again, which is that in order to get a quantum speed up, we're going to design our problem so that there's some structure to the function f, right? We're going to put some structure on our function that makes it easy for a quantum computer to see what's going on while making it harder for a classical computer, right? And since we're the ones inventing the problem, we get to do that. Okay? So here's the Bernstein-Vazirani problem. This already takes us to 1993. Now we're given a black box function f, which maps n input bits to one output bit. Okay, and we are promised that we're guaranteed that f has a special structure to it. Namely, there exists a string, an n-bit string s, which I'll call the secret string, such that for every x, f of x equals s dot x mod 2. Okay? So in other words, I'm promising you that all f of x is it's the parity of some secret subset of the bits of the string x. Okay? And then our problem is going to be by querying f to find s. Okay? So we want to learn the secret string, right? Learn which subset of the n bits is being exclusive ORed together to produce f of x. Okay, questions? Okay. Okay. And if you want another little exercise, they show how Deutsch-Jozsa can be seen as a special case of Bernstein-Vazirani, as the case like n equals 1. Okay? Okay. So how do we find s? Okay, first of all, what about classically? If I have a classical algorithm that can just query one input at a time, how many inputs do I need to query before I can learn s? Can anyone give me either an upper bound or a lower bound on that number? Upper bound is n. Good. How do I do it? Good. Excellent. I just, look at these special inputs. All the inputs of Hamming weight 1, meaning, all the inputs that have exactly 1 1 in them, right? And, each of these queries, well, it just tells me another bit of s, right? This is, this is going to be s dot 1000, which is just the first bit of s. This is the second bit of s, and so on. Okay, so even classically, right, this problem is not that hard, right? It only requires, n queries. Okay, what about a lower bound? Is there a better classical algorithm than that? Anyone? let me rephrase. Could there be a better classical algorithm than this? No, I see someone shaking their head no. Oh, why not? That's exactly right. S, has n bits of information in it, right? That can be varied independently. Okay. Each query in the classical world, at least, can tell you at most one additional bit about S, right? And you really can just formalize that. It's just there's nothing more to it than that, right? You want to learn n bits, you have to make n queries. Okay. So the classical query complexity of the Bernstein-Vazirani problem is exactly n. Okay, now I'm going to show you that the quantum query complexity is, well, it's got to be more than 0, again, but it's not much more, 1. Okay, this, again, can be solved using only one quantum query. Okay. And actually, also using a number of gates that will only be linear in n. Okay, so it's all, so that part will also be efficient, as it turns out. So how do we do it? Well, let's now start with n qubits, since our problem involves a function of n bits. Okay, what should I do first with these qubits? Anyone? Hadamard. Good. All right. Now I've Hadamarded. What should I do next? Query. So let's do again a phase query. Right? What should I do next? Hadamard. Good. See, some of these algorithms just invent themselves. Okay. And then I'll just measure all the qubits in the 0-1 basis. Okay? Let's look at what's happening here. Okay? First step, I just create an equal superposition over all 2 to the n of the inputs. Okay? Just like the popular article said. Okay? Next, then I do a phase query of f. What does that do? Anyone? Huh? Yep. Now, f of x, has gone into the phase. Okay. Now let me just examine, this thing a little bit more. Okay. What is this? Well, we know because we were promised that f of x equals s dot x, right? So I can just rewrite it like that. Okay, which in turn, just by definition, this is like s1 x1 plus x2 s2 x2 plus and so forth. By the way, I don't need a mod 2 here. Why not? Yeah, because I'm raising minus 1 to the power anyhow, right? So I can just say this is equal to minus 1 to the s1 x1 times minus 1 to the s2 x2 and so forth, minus 1 to the sn xn x. Okay? Now I claim that this is actually a separable state, right? This has no entanglement in it, right? Well, these amplitudes factorized, right? So what I'm going to do is I'm going to say, if I just stare at this, I claim that it can be rewritten as follows. I claim that this is nothing other than 0 plus minus 1 to the s1, 1 over root 2, tensor, dot, 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 0 plus minus 1 to the sn 1 over square root of 2. Okay, so these factors, right, are I've just spread them out, and and this, right, all I'm saying is that every time an SI is 1 and XI is also 1, then that is when I flip the amplitude again, right? Okay, so now when I take this state and I Hadamard each qubit, then what happens? Yeah, so this, all this is just saying if S1 equals 0, then this is the plus state. And if S1 equals 1, then this is the minus state, right? Hadamard, the whole point of it is to map between plus, minus, and 0, 1. So so when I Hadamard this state, all I'm going to get is the classical basis state, S1, okay? And S2, and so forth. Okay, voila, my answer, right? And now, okay, here, final exercise for you. How is it possible that our quantum algorithm was able to extract n bits of information from the oracle using only one query that just returned a Boolean answer, right? Doesn't this violate some, information theory, some, Halevo's theorem or something like that, okay? Well, it doesn't, but, you need to think about it a little bit. Okay, so somehow we got n bits using only one query. Okay, so that's a pretty impressive speed up in the sense that is it an exponential speed up? Is it doubly exponential? Well, n grows very, very rapidly as a function of 1. Okay, I don't even know what to call that. That's like a right, that's like a ridiculously, you can't, in some sense you can't hope for a bigger speed up than that. But in another sense, it wasn't that great because the problem was already pretty easy classically, right? We could do it in only n queries. What we really want is a problem that takes something like 2 to the n queries for a classical computer, right? That is exponentially hard for a classical computer, but is only polynomially hard for a quantum computer. So Bernstein-Vazirani doesn't do that, but tomorrow morning I'm going to show you the first quantum algorithm that did do that, which is called Simon's algorithm. And then we'll discuss how by just tweaking Simon a little, we can get Shor's algorithm, okay? And then we'll do Grover, and then we'll see what else we have time for. All right, thanks.
Okay, so we should all proceed now to Farron Field. It's just on your way to C4C. Let's please do it promptly just so people are not taking in the sun waiting for stragglers.
So when you
Yeah.
describe the complexity classes,
Yes.
were you dividing them on the basis of query complexity?
No. Okay, so we're going to talk tomorrow about the relation between query and computational complexity, okay? But basically, what you can do, like when you prove these exponential separations in query complexity, as we'll do tomorrow, right? That doesn't prove that like BPP is different from BQP, right? That would be too staggering, right? Right? As I said, we can't even prove P is not equal to Pspace, okay? But what does it do? What it does is it gives us what is called an oracle separation between BPP and BQP. Because it shows, well, the recent one was BQP versus PH. That's a much harder separation, okay? But what I'll show you tomorrow is what you need if you just want to separate BQP from BPP, which is a much easier question, right? Okay, but in general, when we can separate one model from another in query complexity, then what it gives us in computational complexity is that there exists an oracle that makes the one complexity class different from the other one. Right? Like in lieu of, we don't know how to separate most complexity classes in the real world, right? But often with effort, we can separate them relative to an oracle. And that's, because that really boils down to query complexity.
So you just have an oracle.
Yeah.
Each book can
Yeah, exactly. We say, look, here is an oracle where if I gave classical computer and quantum computer access to this same oracle, then the quantum computer will be exponentially faster.
No matter how
at learning
the
something
oracle
about it.
was
We delay something.
Well, I mean, we'll have to build the oracle in such a way that that is true. But we get to design the oracle to make that true.
So oracle separation is not same as computational complexity. Exactly.
Well, right, that's right. I mean, you know, an oracle separation is typically much easier. But, you know, but, you know, although, you know, often still, you know, requiring years of effort, but, you know, not centuries of effort, right? You know, we can often do that, right? Yes.
So even for the PNP stuff, like
Yes.
people try to use
Yeah, so that was like you know, the whole thing with oracle separation started when Baker, Gill, and Salovey wrote the seminal paper in 1975, where they said, look, you know, we can't prove P is not equal to NP, but we can design an oracle that would make P not equal to NP. Right? That we can show that there exists some relative